Hey guys, this is your 1.7 lesson, trigonometric derivatives. Actually, the derivatives for trig's not that hard, but there's a lot of stuff for trigonometry that I'm going to expect you to remember. And I know that the first time a lot of you guys saw that was last year. So a big part of this video is going to be reviewing trig at the very beginning, and then I'll move into the actual calculus part. You're welcome to fast forward through as much of this as you prefer. The first thing I'm going to be doing is I'm going to go over problems kind of like what we talked about in the 1.6 homework, I think it was. Problems like this. Another thing that I'm going to talk about is how to solve those using the unit circle. I'm going to give you a cheat sheet after that, but I want you to know how to do it using the unit circle too, because it's a good skill to have. Second of all, we have some trigonometric identities that I think might be helpful for you guys to remember. Okay, so that's what I'm going to do. Is we're going to do a quick review. Well, I don't know how quick it'll be, but I am going to spend some time doing some review. Next time you guys see this pop up on the screen, though, that's when I'll be beginning the actual lesson for calculus. Like I said, watch as much of this review lesson as you prefer. Fast forward to the calculus part as you see fit. Okay, so I'm going to go ahead and begin here. So we need to know how to evaluate trigonometric expressions. So to do that, let's go ahead and jump over here to our unit circle. Now, when we're on our unit circle, we have sine of theta, and theta represents an angle of some kind. In calculus, it's always going to be radians. So all these degrees here, I'm just going to X them out because we won't be using degrees in calculus. We always use radians. The sine value of any radian value always gives you the y coordinate on the unit circle, whereas the cosine value will always give you the x value on the coordinate circle. Okay. Now the tangent value at any given point is, well, it's y over x. A lot of times I feel that it's pretty helpful just to have those already filled in on the unit circle. So I'm going to go ahead and put those on there right now. So for instance, if you were to wonder what's tangent of pi over 6, it would be this green value I put here, radical 3 over 3. And there's a pattern here. It's a very simple pattern. You really only need to know about 5 different numbers here. So radical 3 over 3, those are always the ones that are closest to the x-axis. So for instance, this one, this one, this one, and this one. Those are the ones that are closest to the x-axis. Those are the ones that are radical 3 over 3. Let me get rid of those circles real quick. The ones that are closer to the y-axis, those are radical 3. So here, 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 here. And of course, the middle ones are all 1, in case you haven't noticed. So like, for instance, right here, the middle of this quadrant, this angle here, pi over 4, that's a 1. Same thing over here. You'll notice there's also some signs, right? Everything on this quadrant and this quadrant are positives, whereas everything on the other 2 quadrants are negatives. So some patterns there. Tangent equals 0 when you're at 0 radians, or at pi radians. The tangent value is 0. If you are at pi over 2 radians or 3 pi over 2 radians, the tangent value is undefined. It doesn't exist at that point. Okay, so sine gives you the y value, cosine gives you the x value. So these are the x's and y's for each one of the radians that they'll be giving us. And tangent, you don't really need this fact now. It's just the green stuff. So, and I have trouble finding unit circles where they actually have the tangent values on there. I think it's really kind of a pain in the butt to make kids figure it out every time. So I just tell them to memorize it. It's a few easy numbers to remember. But there you have it. So now let's go ahead and continue our journey here a little bit. let's talk about secant. Secant of theta is basically the reciprocal of cosine. You can also think of that as 1 over x then, right? Cosecant is the reciprocal of sine, which you can think of as 1 over y. In other words, just take the answers for x and y and flip them over. And then finally, cotangent is the reciprocal of tangent. Okay, so we need to know those things to do the exercises that we're about ready to do. So let's go ahead and do a couple of these problems real quick here. So let's suppose for a second I asked you, what's cosine of 5 pi over 3? So the first thing we're going to do is we're going to notice that it's asking for the cosine. So they're asking here, what's the x value when theta equals 5 pi over 3? So we're going to look at our unit circle, and we're going to find what's the x coordinate when theta equals 5 pi over 3. So we have to find 5 pi over 3, which is right down here, and the x value for that is 1/2. And so that would be our answer. So last year in your Trig pre-calc class or your Geo-Trig class, you hopefully had memorized that. Now I'm sure that many of you guys have forgotten it. You may want to consider taking the time to refresh your memory so that you know how to do these things quickly. Okay, let's do another one really quick. How about sine of pi over 2? Well, when you're talking about sine, they're asking what's the y value when, in this case, theta is pi over 2. So what's the y value when theta is pi over 2? So here's pi over 2, and the y value is 1. So that would be our answer for that one. Okay, now let's do another one. How about tangent? We're just going to do an example of a couple of them just to kind of make sure you guys have seen all the possibilities here. So suppose I had tangent of 4 pi over 3. Tangent of 4 pi over 3. So I'm going to find where 4 pi over 3 is on my unit circle. I'm going to find the tangent value that goes with it. So let's do that really quick. So 4 pi over 3 is right here, and the tangent values are the ones that I did in green. They're right here. So the answer to this one would be radical 3, a positive radical 3. So when it comes to sine, cosine, and tangent, it's really just as easy as finding the angle and then finding the number that goes with it, whether it's an x value, a y value, or a tangent value. Well, let's go ahead and jump into the reciprocal ones. So suppose I asked you guys to tell me what is secant of 2 pi over 3. Okay. Well, secant is the same thing as 1 over cosine of 2 pi over 3. So what I want to do then is I want to find what where 2 pi over 3 is, and I want to find the x value, because it's cosine, that goes with that. So let's go ahead and go to our chart now and find where 2 pi over 3 is, and find the x value that goes with that. So here's 2 pi over 3, and the x value that goes with that is -1/2. So let's go ahead and go back now. We have a little bit more work to do, though, with these reciprocal ones. So what I have now is I've got 1 over, and that cosine of 2 pi over 3, that's negative 1/2. So now we need to simplify that. And this is what's called a complex fraction. It's when you have a fraction inside of a fraction. So the way that I handle those is I usually multiply the bottom fraction there by its denominator, which is 2. That way those cancel out. And you're allowed to do that so long as you also multiply the top by that number as well. So I end up with 2 over negative 1, which is negative 2. So the final answer for secant of 2 pi over 3 is that. Now there's a much faster way to do that, okay? The faster way to do that is just to know that secant is the reciprocal of cosine, right? So what's cosine of 2 pi over 3? It's negative 1/2. So therefore secant would be the reciprocal of that, negative 2. So you don't have to do all the steps I just showed you. You can just take the answer for cosine and flip it over. So you could say, what's the reciprocal of cosine when theta equals 2 pi over 3? Okay, now cosecant is pretty similar. Cosecant is the reciprocal of sine. So suppose I gave you guys this. Cosecant of 5 pi over 3. Cosecant of 5 pi over 3. Well, since cosecant is the reciprocal of sine, which I wrote on another page somewhere else, what that means is we're going to find what the sine value is, the y value, and take the reciprocal of it. So what is the reciprocal of y when theta equals 5 pi over 3? So let's go ahead and go take a look at our circle again here. So 5 pi over 3 is right here. And here's my y value. Now I want the reciprocal of that. So what this will be then is negative 2 over radical 3. That's the reciprocal of the y value. And just so you guys know, they don't usually leave the answer like that because you're not supposed to have square roots on the bottom. So what you're supposed to do when there's a square root on the bottom is you're supposed to multiply the top and the bottom by that square root. Because the square root of 3 times the square root of 3 is just 3. The square roots cancel out and leave just the number. And then you have 2 radical 3 there. Okay? And so that would be how you'd write your answer. We'll do one more problem here, and that'll be cotangent. So let's talk about a cotangent really quick here. So suppose that I asked you guys to find cotangent of pi over 3. Well, cotangent is the reciprocal of tangent. So what this is saying is, what is the reciprocal of tangent when theta equals pi over 3? So let's go ahead and find pi over 3. We're going to find the tangent value, and we're going to do its reciprocal. So here's pi over 3. The tangent value is radical 3, and we're going to do its reciprocal. So what's the reciprocal of radical 3? Well, if you think of it as radical 3 over 1, the reciprocal of that would be 1 over radical 3. And once again, we don't like leaving that square root on the bottom, so we multiply the top and the bottom by radical 3, which gives us radical 3 over 3. Okay? So that's how you can find sine, cosine, and tangent for any angle. Now there's something else, though, that you guys might want to be aware of. Negative angles. So the way that negative angles work is when we're on our unit circle, we always think of angles as starting here and going this way in a counterclockwise fashion. So we start at 0 degrees or 0 radians, and then we go to pi over 6 radians, and then we go to pi over 4 radians, and then we go to pi over 3, etc., etc. And that's going this way. But if you go the other way, you get the same thing, just negative angles. So if I go this way, then right here would be negative pi over 6. Right here would be negative pi over 4. Right here would be negative pi over 3. This one would be negative pi over 2. And it just keeps going. So it's like a mirror image, top to bottom. So if you compared this spot here with your regular unit circle without the negatives on it, that angle is also in a positive form. You could say that's 11 pi over 6. So those are what we call coterminal angles. They're the same spot in the unit circle. This is the positive version and this is the negative version. But that's what negative angles are. So let's go ahead and do an example that has a negative angle in it, and then we'll kind of see how to work that out. So suppose that I asked you guys to do tangent of negative, how about 7 pi over 6? Okay, well, let's go ahead and take a look at our unit circle and see where that would be at. Okay, so if I was going this way, starting here on my unit circle in the initial position and going this way, 7 pi over 6 is right there. So I went halfway across my circle and then one more spot, right? But we want a negative angle. So to do that, we're going to go halfway across our circle plus one more spot. So negative 7 pi over 6 is this angle right here. So it's the same thing as that one. So you use that symmetry to think of it as a different spot, right? So let's go back to this now. So tangent of negative 7 pi over 6, that's going to be the same thing as tangent of 5 pi over 6. Because these two angles, negative 7 pi over 6 and 5 pi over 6, are what we call coterminal. Okay, so now let's go back again. Now that we're going to do tangent of 5 pi over 6, what is it? Tangent of 5 pi over 6 is negative radical 3 over 3. So that would be our final answer. And by the way, I'm just kind of being extra here. You didn't really have to write this. I mean, you could have just saw that the answer was radical 3 over 3 to begin with. I think it was negative, though. So there you go. So that's how you evaluate trigonometric expressions. Okay? Been a while for you, but hopefully none of that's new. Hopefully all that is something that you guys have seen before. Now, I'm going to show you something that's going to make you guys angry. And you're going to think, well, why the heck didn't you just show us that to begin with? The reason I didn't show it to you to begin with is because I think it's important that you guys know how to do this and review these things. But we have some answers right here also. So for instance, if you wanted to find what's cosine of pi over 6, just find pi over 6 and go to the cosine, and there it is. All right, so now you're mad at me, right? It even works for the secant, the cosecant, and the cotangent. I had to make a few corrections because this place that I printed it out from had some wrong answers on it. But there it is. You guys can use this. I'm totally okay with that. But the problem is, though, is that when you guys are taking your AP exam, on the FRQs, it doesn't matter because you don't even have to do this. You can just leave your answers as, you know, for instance, as we saw earlier. Let's see if I can draw on here real quick. You can just leave your answers like this. You don't even have to. It's not letting me draw. Oh well. Anyway, you can just leave it as, like, for instance, cosine of pi over 4. You don't have to get the actual answer for a free response. But on a multiple choice, you do. But you're not going to have this chart in front of you on your test. You need to know how to figure it out. So even though I'm giving you guys the reference sheet here to make life easy, you really should be taking the time to know how to figure these out, because come test day, if you don't know how to, that could be a problem for you. That could be a problem for you. All right. Now, other than that, I have another reference sheet I want to share with you guys, some things that what we call trigonometric identities. I've already shared some of them with you, like sine is 1 over cosecant, cosine is 1 over secant, or vice versa, cosecant is 1 over sine, secant is 1 over cosine. Tangent is the reciprocal of cotangent, and vice versa. So what does this mean? This means that if you ever see a expression like cosecant, you can replace it with 1 over sine, because those are equivalent expressions. They're identical things. So we call them identities. Here's another one. Tangent can be replaced with, up here I said tangent can be replaced with 1 over cotangent. You almost never are going to use this one, by the way. Matter of fact, let me bring up something here. I just want to show you. These things are all true that I'm sharing with you. However, you're not going to use some of them very often. So let me show you the ones you're not going to use. Clear out this fun stuff off. You're not going to use this almost ever. You won't be using this almost ever with this. The bottom ones you might. You'll definitely use these a lot. This one sometimes. These guys you'll use a lot. So tangent is sine over cosine. Cotangent is cosine over sine. You want to know those. These are called Pythagorean identities down here, these guys. As for these are nice to know if you want to be like a pro, but this is kind of the ones that they are pretty common. You want to know those ones. Okay. Other than that, there's a lot of identities in trigonometry, but when I teach trigonometry in my pre-calculus class, these are the only ones I really even focus on, because the other ones are used so rarely that it's kind of like these are hard enough to get anyway that I just focus on these. Does that make me a bad teacher? I don't know, but that's it. So you guys have these resources. You have this trig identity worksheet. You might want to print that out. You might want to print out a unit circle for yourselves, and you might want to put the tangent values on there. And you'll probably really love this, but you know, it's kind of like, should you watch TV or do your homework? TV, homework. Easy, hard. Not going to help you on the test. This will help you on the test. So it's up to you. Do as you will. But there's our trig review. So having gone over that, I'm going to go ahead and move on into our lesson now. So there it is. Let's begin our lesson on trigonometric derivatives. So we're going to do derivatives of trig functions today. Let's go ahead and jump in. Here they are. What is the derivative of sine? Well, interestingly enough, it's cosine. So, for instance, if you wanted to find the slope of this function, y equals sine of x, right? If you wanted to find what's the slope of this function at x equals 0, what you would do is you would take the derivative of sine, which is cosine, and you'd plug in 0, and then you use your unit circle. You would look for the x value when you're at 0 radians. And the answer for that would be 1. Okay, so these are the derivatives of the trig functions. They tell you the slope of the trig function. So what's the derivative of cosine? It's negative sine. Okay, so these kind of go together, don't they? The derivative of sine is cosine. The derivative of cosine is negative sine. All right, let's take a look at another one. The derivative of tangent is secant squared x. So in other words, the slope of tangent is secant squared x. All right. The derivative of cotangent is negative cosecant squared x. So these kind of go together too, in a way, right? They're both the tangent ones. So derivative of tangent is secant squared. Derivative of cotangent is negative cosecant squared. You'll notice something, that tangent and secant go together here, right? When we get over here, you're going to see they go together again here. Same thing with cotangent. Cotangent seems to go with cosecant, and that seems to happen again over here. So in your mind, to help you remember it, it's kind of helpful to know that for some reason, secant and tangent are good friends, and cotangent and cosecant are good friends, right? So now the last pair is the derivative of secant and derivative of cosecant. The derivative of secant is secant tangent. The derivative of cosecant is negative cosecant cotangent. Now you'll notice that some of these are negative, right? Some are not. Take a look at all the ones that are negatives. There's one, and there's one. They all have something in common. Just coincidence. It's a good coincidence, but it helps remember it. All of them start with a co, like cosine, negative. Cotangent, negative. Cosecant, negative. All these other ones that don't start with cos don't have negatives. So just some patterns in how the derivatives are so that it helps you memorize them. But ultimately, you're going to want to make some flashcards for these, you guys. This is a great time to start making flashcards. Now, the good news is, if you picked up your notes from the library, I've actually already made the flashcards. They're in the very back of your notes handout. All you need to do is know how to cut them out and put them together. And I would start quizzing yourself regularly on these derivatives. So there you guys have it. Those are the trig derivatives. So now we're going to begin. Now, I'm not going to give you a question like this for today anyway, because that would be pointless. If I gave you this and I said, okay, what's y prime? Well, that's a pretty lame question, because all you have to do is go, oh, okay, well, I'm going to go back here, cosine. Well, the derivative of cosine is negative sine. So then my answer is negative sine. So basically, I'm not going to give you a question like that, because you would just be copying the things right off the previous slide. That's not going to help you learn anything. It might help you memorize it, but that's something you can do with flashcards. So instead, what I'm going to do is I'm going to make you do the trig derivatives, but combining the trig derivatives with all the derivative rules we learned last week. So we've learned 4 of them. We've learned the sum and difference. We've learned the product rule. We've learned the quotient rule. We've also learned the chain rule. Now here's what I want you guys to do. I want you to draw a line from this side to the equation on this side that it goes with. So which one of these functions over here is a sum and difference rule? Draw a line from here to that one. Pause the video and connect a line for each item on the right to one of the equations on the left. And when you unpause it, I will show you what you should have gotten. So the sum and difference, that's when you have 2 functions being added together. So that's this one right there. The product rule is when you have 2 functions being multiplied. So that's this one right there. The quotient rule is when you have 2 functions being divided, which is this one right there. And a chain rule is when you have an inside function, something inside the parentheses, which is that guy right there. So that's one thing you're going to want to know how to do for your homework, is you need to know what rules to apply to these trig functions. All right, so let's go ahead and begin. Let's do the sum and difference rule to this one. So according to the sum and difference rule, all you do is you take the derivative of each piece. So what's the derivative of sine? Well, let's go ahead and just flip back a little bit. Derivative of sine is cosine. So the derivative of sine is going to be cosine. Plus, now we do the derivative of cosine. What is it? Let's flip back. Derivative of cosine is negative sine. So now I'm going to put a negative sign there. And to write it in simplest form, we don't really need to write plus a negative. So what we'll do is we'll just put minus in between them. And there's the derivative of r. So the sum and difference rule, just take the derivative of each piece and you're good to go. Okay. As we go, I kind of want to let you guys do one after I do one. But I don't think I gave you guys a sum and difference on your student practice. So we'll skip that for now. Let's go ahead and jump on to number 2. Let's do this one. This was the chain rule. So in case you forgot, the chain rule is the derivative of the outside being multiplied by the derivative of the inside. Now the outside function here is the tangent function. The inside function is the x squared. So let's do the derivative of the outside function. The derivative of tangent, well, if we flip back to the previous slide, the derivative of tangent is secant squared x. So the derivative of the outside then is going to be secant squared. And instead of x, we're going to use the inside that we have, right? Don't change the inside. And then we multiply that by the derivative of the inside, which is 2x. And usually when you write these, the monomials, 2x, goes in front of the more complicated parts of the expression. So there's our final answer for the derivative of wx. So that's a chain rule. And I did give you some chain rules on this next one here. So let's switch sides really quick. I want you guys to pause the video, and I want you guys to try to do number 2. Pause the video and do number 2. When you unpause it, you will see this worked out solution. Okay, so there's our answer. The derivative of the outside function, which is sine, is cosine. So we have cosine of 3x now instead of sine of 3x. And then the derivative of the inside is 3, so we put a 3 in front. So the final answer is 3 cosine x. Now, the next one that we're going to do another one here. I want you guys to do number 4. But before I let you guys just go ahead and start, I'm going to do the first 2 steps with you, and then I'm going to let you guys do the rest, okay? Because this one can be a little bit challenging. So first of all, as you guys might recall, we don't like, when we're trying to do derivatives, we don't like these radicals. We like to rewrite them as powers. So this is a square root. And so what that means is the first thing we're going to do is we're going to rewrite that as instead of taking the square root of the whole thing, we're going to raise that to the half power. Here's where something's going to come in that you might not have thought to do, but it helps, and it's easier if you just do it, is we're going to do an old pre-calculus rule. What do you do with 2 exponents when you're raising one power to another power? You multiply them. So that's going to look like this then. Now, you didn't have to do that. There's a way to do this problem without doing that, but it would become a lot harder if you didn't. So I'm going to leave it at that. Now, at this point, it's a chain rule. But I want to remind you guys of something before I set you loose on the problem. It's an egg problem because it's a double chain rule. You have the egg shell, the very outermost function, which is something being raised to the 3/2 power. You have the yolk, which is the innermost function. And then you have the egg whites on the inside, which I'll do in purple here. So you have an outermost function, an innermost function, and a medium function. So when you do your derivative, you're doing a double chain rule. So you do the derivative of the outer, middle, and inside multiplied together. So go ahead and work it out, see what you guys get. Pause the video here, and when you unpause it, you'll see this. Okay, so here's the answer. The derivative of the outermost function is 3/2 of the inside to the half power, because if you take 1 away from 3/2, you get a half. The derivative of the purple is going to be cosine. The derivative of the yellow is 2. So if I multiply 3/2 by 2, I get 3. And so now I'm going to put the 3 in the cosine 2x in the front, and I'll put the sine 2x to the half power in the back, and I'll also change the half power into a square root. Okay, so there's your final answer for the black one there. Let's go ahead and go back now to another example problem. Let's do the third one down. We decided this one was going to be a product rule. Okay, so let's do that. So what's the product rule? The product rule works like this. You have A, B, A, B, right? You guys might notice I switch. Like sometimes I'll put the derivative here, sometimes I'll put it here. All that matters is that one pair has a derivative and the other pair has the opposite derivative. It's right either way, which means that the order of these things doesn't really matter, just so you guys know. All right, so let's do this. So I'm going to say that cosine is my A, and I'm going to say that tangent is my B. So what's the derivative of my A? Well, the derivative of cosine is negative sine. And then we're going to put B. Then we have A. And then we have the derivative of tangent, which is secant squared theta. Now this answer is fine, just as it is, okay? But I want to show you guys some things that might happen. It doesn't happen often, but it could. I've seen it, where they use the identities. So as you guys know, tangent can be written as 1 over cotangent, or it can be written as sine over cosine. Now, there's really no reason for me to do that, though, because if I were to replace tangent with one of these two things, it's not going to really make any difference. It'll actually just probably make it look uglier. So I'm going to leave that alone. But something interesting happens over here. Secant squared. Well, secant is 1 over cosine. So secant squared would be 1 over cosine squared. Now, the reason why that's interesting is because if I were to replace secant squared with I don't know if I can carry this. I'm going to try to. Well, let me. If I can replace secant squared with 1 over cosine squared, then we can kind of simplify this a little bit. Cosine times cosine over 1 over cosine squared is going to look like this, right? And why is that significant? Well, let's go ahead and move it on up there. I don't know if it's going to let me move the whole thing. I'm trying to be creative here. What is that? This is going way out of where I wanted it to. There we go. All right. There's that, right? Now, what's cosine over cosine squared? Well, the cosine on the top will cancel one of the cosine on the bottom, so we end up with 1 over cosine, which you can rewrite that as secant. So, I just used the identities a little bit to write this expression a little bit simpler. Cosine times secant squared, because secant squared is really just 1 over cosine squared, just simplifies to basically secant theta. So, it's possible on a multiple choice test that they can ask you a question like that, do something like that. Anyway, let's go ahead and have you guys try one. I don't think yours is going to come out quite that crazy, but the main thing is do the trig derivatives and do the product rule. So go ahead and pause the video here and do number 1. Do your trig derivatives and do the product rule. And if you can, try to simplify it. So if you guys got this far, I'm pretty happy. Just this first step even, that's pretty good because that tells me you know how to do the product rule. It tells me you know how to do the derivatives of trig functions. But we can simplify this a little bit. Sine times sine is sine squared, and cosine times cosine is cosine squared. Now the negative here in the front, right, is there. And we don't usually like to write expressions with the negatives in the front, so I rearranged it so it's the positive in the front, so it's cosine squared minus sine squared. But honestly, any of these 3 answers are good and correct. Okay, let's go ahead and do one more. Now, this next one's going to really throw you for a loop because mine's going to be challenging, but that's okay. I want to challenge you guys a little bit. It's the quotient rule, right? Now, we know that the quotient rule is as follows. Low d high minus high d low. Draw a line and square below. So the squaring below is pretty chill. That's done. The issue is the top here. So let's do low d high. I'm going to leave that for now. We'll come back to it. But that means we want to do the derivative of the top function there. And then we do high d low, which we'll also put a little question mark there for. So the issue here is finding the derivative of the top and the derivative of the bottom and putting your answers there. A little bit more challenging than it looks. So I'll do the derivative of the top, and then I want you guys to try to do the derivative of the bottom. So here we go. First of all, I want you guys to understand this. When it says that cosine is squared x, what that really means is that they're taking the cosine function of x and they're squaring it. I like to write it like this because it makes it look more like what it really is. That's actually a composite function, so that's a chain rule. Okay, so what we have then is we have an outer function, which is something squared plus 1, and our inner function is cosine. So the derivative of the outer function, you're going to multiply the 2 to the front, take 1 off the power, it's just going to be 1 now, and the derivative of 1 is 0, so that goes away, times the derivative of the inside, which is cosine. The derivative of cosine is negative sine. You don't want to put the negative here because if you do, that makes it look like it's saying cosine x minus sine x. It's not. It's cosine x times a negative sine x. And so what we're going to do, since we're multiplying it, just put the negative in the front. So that would be the derivative of the top. So it's really a sneaky little chain rule because cosine squared x really means cosine x to the second power. Okay, so I'm going to go ahead and put that answer in there. What I want you guys to do is pause the video after this and see if you guys can find the derivative of the bottom. So let me put this in here real quick. Go ahead and pause the video and see if you guys can find the derivative of the bottom function now. So sine squared x really means sine of x squared, so we have a composite function. We're going to multiply the 2 to the front. We're going to take 1 off the power, so now it's just sine x. And then we do the derivative of the inside function. The derivative of sine is cosine, so we have 2 sine x cosine x. And that's what you guys are going to go ahead and put over here in this blank. So we did low d high minus high d low. We drew a line and we squared below. Now I'm going to do something that's even more irritating to you. I have to write it underneath, but that's just because I ran out of space. It's actually supposed to be next to it, so be careful with that, you guys. That didn't work out well. What was that? Got an extra stray mark there. Okay. Now I'm going to do something that kind of bugs a little bit, and what I'm going to do is I'm going to do some algebra. And algebra is kind of going to bug you here a little bit. So let me make some writing space. I'm actually going to do some algebra and some trigonometry, both of which are a little bit challenging. Now, what I'm about ready to do is going to be irritating to you because you're going to think, Mr. Bailey, how the heck would I have known to do that? Well, you probably wouldn't have, and that's okay. It's stuff that you should have learned before, but that doesn't mean you're going to remember it. It's pretty obscure stuff. So before I begin this, I want to remind you guys of some basic algebra stuff here. So if I gave you guys this, you guys hopefully remember how to take out a greatest common factor. What do these two terms have in common? They both have an x, so you can divide that out and write it like this. That's called taking out a GCF, right? So we're going to do something a little bit like that. Well, let's look at this expression that we have right now. And I want you guys to compare this half with this half. You notice that they have something in common? They both have the same factor there. They both have a 2 cosine x. What I'm going to do is I'm going to factor that 2 cosine x out. So if I do that, here's what I'm going to get. So if I take that out, this front half here will no longer have the 2 and the cosine x there. It'll have the negative, so don't lose that negative. And I'm going to move it to the front. And then minus. This whole thing's gone. And I'm left with cosine squared x plus 1. All over the bottom still. Nothing's going to happen on the bottom right now. I've seen this move done a lot in calculus, some calculus texts. So knowing how to recognize the common factor there and take it out is actually a pretty good skill to have. I probably won't be torturing you guys too much with stuff like that myself, but it could pop up in our review sessions when we look at AP-style questions. It's not real common, though, just so you guys know. So don't feel bad about not understanding this 100%. Just do the best you can. So I'm going to distribute the negative in here, and I'm going to distribute the negative in here as well. So now I'm going to have the following. Kind of getting sick of writing all this stuff. It's like we're in calculus or something. Huh. Funny, Mr. Bailey. Okay. What the heck? Alright. I'll clean this stuff up as I go so we don't get overwhelmed. Okay. Next, we're going to go ahead and we're going to simplify the inside a little bit more here. How about negative 1, negative 1? That's negative 2, right? Now, if I was really solving this on my own, I probably wouldn't show every step like this. I would do a lot of this in my head. You guys are welcome to do the same. But when it comes to teaching, I got to make sure I show every step just because different people have different questions. All right. Now, go ahead and continue. This here is interesting. I'm going to do another little ninja move that's not at all obvious, but I'm going to do it. Notice how both of those are negative? Since they're both negative, I'm going to take a negative out. And you guys are like, oh my gosh, Mr. What the heck? Don't worry about it, guys. Just follow along and understand it. Don't think, oh my gosh, I have to do that. Well, not quite. This is very tortuous. Why did I do that? Why did I take that negative out? This is one of our identities. If you look at the little identity sheet that I shared with you guys during our review session, what did that come out to equal? That equaled 1. So, this whole thing right here is 1. So I can replace that with 1. And there's a negative in the front, so don't forget that. So negative 1 and negative 2 is negative 3. And since I'm multiplying that negative 3 times this, just put it with that 2, and we're going to get negative 6 cosine x sine x over sine squared x plus 1 squared. Okay, so I tortured you. I showed you guys a lot of algebra, but they're good moves. You need to know how to use identities. You need to know how to do factoring. So those are some things that will come up occasionally. This problem was literally a nightmare. I wouldn't put something like this at you guys on a test without preparing you for it, but a lot of stuff there that's of good use. So here's what I want you guys to know how to do for your next problem. So I'm going to have you guys do a quotient rule. It's this one right here. For yours, it's much easier. Okay. Just do the quotient rule. If you can get that far, I'll be happy. But you can also simplify it. So see if you can simplify it a little bit. The simplifying is definitely not as hard. The quotient rule is not as hard as the one I did. But just go ahead and do the quotient rule. And if you can, try to simplify it as much as you can. Pause the video, and when you're done, you will see the solution. Okay, so if you guys got this far, then you're right where you need to be for the day. If you got down to here, you're keeping ahead of the game a little bit. So these two terms here had something in common. I could divide a 2x squared out of both of these terms. If you take 2x squared out of there, I should have had an x in the front there actually. If you take 2x squared out of the front, you're left with an x, secant squared x. And if you take a 2x squared out of here, you're left with 3 tangent x. And then the bottom, 2x cubed squared, that becomes 4x to the 6th. And then you reduce this top monomial with the bottom monomial, and you get this final answer there. Okay, so there you guys have it. So that's derivatives with trig functions. We're going to do one more thing. I know this lesson's kind of long. It's because of the review section in the beginning, and it's because I know that we always need review with trig. But our lessons aren't always that long, so bear with me. We have one more example we're going to do. I think it's example 2. And then I'll let you guys practice one and we'll be done for the day. All right, so here we go. Find the line tangent to the function at the given point. So here's my function, and here's the point. Okay? So what they've given us then is they've given us an x value and a y value. And if I'm trying to find a tangent line, that means we need this, right? The good news is they've already given us most of the stuff we need. They gave us the x1, they gave us the y1. All we need now is the slope. So what I need to do then is I need to be able to find the derivative of this cosecant here. So there's a couple things going on with this cosecant. So let's first of all notice that this is a chain rule. We have an outside function, which is negative cosecant and we have an inside function which is 2x. So let's go ahead and let's review really quick. What is the derivative of cosecant? The derivative of cosecant is negative cosecant cotangent. So the derivative of the outside is this negative comes down, and then the derivative of cosecant is negative cosecant cotangent. Now, you guys might be wondering, what's with the double negatives? Well, this one was here to begin with, but when you take the derivative of cosecant, you get another one right there. Okay, so now we have these double negatives. Notice the blanks, because I know that the derivative of cosecant is cosecant x cotangent x, but remember, we have an inside here, so it's not going to be x, it's going to be 2x. And then we multiply it by the derivative of the inside, which is 2. Now, this always gets people. People are like, wait a minute, there's 2 of them. Do we have to do it twice? And the answer is no. This is the derivative of the outside, and this is the derivative of the inside. So, no, you don't need to take the derivative twice of the inside. It's just once. Okay, so the negatives cancel, right? And the 2 goes in the front. So here's my derivative. Y prime is equal to 2 cosecant 2x cotangent 2x. So we're getting there. Now, I have my x1, I have my y1. I'm trying to find my slope. Step 1 is to find the derivative. I did that. Step 2 is to plug in the value that you're working at. We're working, what x value are we working with? Pi over 3. So I'm going to plug in pi over 3 now. Now, you can use your unit circle chart and figure it out. I would encourage you to do that. Or you can cheat and use the reference sheet. I know you guys are all going to cheat. But remember, that's going to hurt you on multiple choice time. But anyway, go ahead and see if you guys can figure out what cosecant of 2 pi over 3 and cotangent of 2 pi over 3 is using your unit circle, preferably, but if you must, you may use your cheat sheet, and I'll put the answers up when you're done. All right, so cosecant of 2 pi over 3, you guys should have gotten 2 pi over 3. And for cotangent of 2 pi over 3, you should have gotten negative radical 3 over 3. All right, now we're going to simplify. 2 times 2 is 4. Radical 3 times negative radical 3 is negative 3. So we have 4 times negative 3, which is negative 12 on the top. And on the bottom, 3 times 3 is 9. And then that reduces to be negative 4/3. So 2 times 2 is 4. Radical 3 times negative radical 3 is negative 3. So 4 times negative 3 is negative 12. Bottom, 3 times 3 is 9. So we have negative 12 over 9, which reduces to negative 4/3. So we're ready to go ahead and write our tangent line. We're going to put our 4/3 right here. We're going to put our x1 here. And we're going to put our y1 here. Matter of fact, it's negative, so I'll just erase the plus there as well. Put minus 2 radical 3 over 3. And that's an ugly hot mess, so I'm not going to simplify it. We're just going to leave it like that. Okay? So that's the equation of the tangent line. So just to kind of give you guys a visual of what we just did, here is the graph. The red lines are the graph of negative cosecant of 2x. And the point where we're finding a tangent is right here. That's the point pi over 3 comma negative 2 radical 3 over 3. And then the blue line is the tangent line, which is the answer I had at the top earlier. So that's what we just did. So finding the tangent line is just like normal. It's just that now you have to do derivatives of trig functions. And you have to know how to evaluate trig functions at points using what we reviewed at the beginning. All right, so here's one for you. Go ahead and pause the video and see if you guys can find the tangent line of this. Now, this is going to be substantially easier than the one I just did. But I want you guys to try to do it. It doesn't mean it's going to be easy. It's just easier than the one that I did. So give it a try, see what you guys get. When you unpause the video, you'll see the solution. All right. So x1 is pi over 4, y1 is 1. My function is tangent. The derivative of tangent is secant squared x. I'm going to plug in the pi over 4, the x value, to find the slope at that point. So plug in pi over 4, we get this. Now, secant of pi over 4 is the reciprocal of cosine at that point. Now, the cosine is radical 2 over 2. So the reciprocal of that, if you simplify it, is radical 2. So secant of pi over 4 is radical 2. And since we're squaring it, radical 2 squared is going to be 2. So the slope should have come out to be 2. And so now we can write our tangent line, the slope, 2, times x minus x1, which is pi over 4, plus y1, which is 1. And there you guys have it. So that's the end of that long and grueling lesson. We'll see you guys for the next one.